Assalamualaikum warahmatullahi wabarakatuh and a very good day to Dr. Hidayah. So we from group 5 will explain about the minor losses experiment 3. So this is the members of group 5: Alethea HANDRALITA AGUS, AMIR ZHARFAN bin ABDURRAHMAN, FELIX SALIM, MOHAMMAD ALEEF bin Patrick, and SITTY ZHAQIA AZZAHRA. So this is the table of contents. So we will proceed to the first part, which is objective. The objective of this experiment is to determine the loss coefficient KL and minor head loss HLM in pipe components fittings for different water flow rates, pipe diameter, and pipe bands. So I will pass to the next person. Thank you.
Hello, my name is Alethea HANDRALITA AGUS. I will continue with introduction part. Friction between the fluid and the pipe walls as well as internal friction between fluid particles are the main causes of energy losses in pipe flow. This experiment measures small head losses through a piece of pipe with numerous bands, transition, and fitting any site in an assembly pipe system where streamline don't seem to be right, such as pipe connection, band, valve, contraction, and expansion, as well as reservoir inlet and output result in minor head losses. The minor or modest losses in pipe are one of the most important pieces of information when constructing a piping network. When a smooth water flow is interrupted by a variety of piping network components such as fitting, valve, band, and elbow, small losses in the pipe occur. This element result in additional losses because friction continuously loses energy which change the pressure value. Next is theory part. For theory part, head loss in a piping network caused by friction between fluid and internal surface of constant diameter pipe along with the friction between adjacent fluid layer can be calculated by using Bernoulli equation. As a result, energy will continuously transition from desirable mechanical form like kinetic or potential energy to less valuable thermal form including heat, friction head loss, which describe the amount of energy transformed into heat per unit of weight of the fluid is the common name for this shift in energy. So we can simplify the boundary equation and then, of course, we will use the condition that's at Z1 equal to Z2. Next is minor losses as sudden enlargement. When a fluid flows through a sudden enlargement from a small conduit into a larger pipe, the fluid velocity suddenly drops, generating turbulence and an energy loss. The formula is K equal to 1 minus A1 over A2 squared. Second, minor losses as sudden contraction. When a fluid flows from larger pipe into small pipe through a sudden contraction, the small pipe's sharp corner will cause a turbulence region that extends beyond the vena contracta, which will cause fluid streamline to converge just downstream of the small pipe. This energy loss producing phenomenon is known as vena contraction phenomenon. The formula is 1 minus AC over A2 squared. The value of KL is dependent on the fluid property including RE, and the geometry component can be denoted as KL equal to geometry. In most practical cases, the KL components are a function of geometry only. In this experiment, the KL value and the HLM in pipe for different water flow rate, pipe diameter, and pipe band will be determined. KL for sudden expansion or enlargement and contraction in circular duct pipe are shown in the figure 1. Note that losses for a sudden expansion or enlargement are based on speed of flowing medium at region 1, 1 over 2 V1 square, whereas for a sudden contraction are based on speed of flowing medium at region 2, 1 over V2 square. When it contracts, as you can see, the fluid has less space to go to. That is why we are using the second velocity, and then for expansion, we use the initial velocity as the fluid has more space. When it gets to the area, you can see the contraction of loss coefficient is very high because lot of losses at this scenario. The contraction because when you suddenly restrict the area of flow of the fluid, it causes a lot of friction and it causes a lot of turbulence in better ways. And then expansion, in case of expansion there are also turbulence but there are less compared to the contraction, which is why the coefficient loss is very low compared to the contraction. So we can get KL value from flow through a sudden expansion or enlargement and contraction from the continuity equation and the momentum. For elbow pipe bends and pipe branches. The value for HLM and KL involving the elbow pipe bends and pipe branches can be experimentally. The next tested geometrical is elbow pipe bends and also branches. The value of minor head loss and loss coefficient for the flow involving pipe component or fittings such as elbow pipe bends, pipe branches are determined by using equation 3 to equation 5, which I have talked about just now, and then the theoretical value of KL for various components of fitting can be determined using this figure. Here are some typical values of KL are certain type of fitting. For example, we have elbow, which is 90 degree, is 90 degree. As you can see, the value of coefficient loss differentiate according to the degree of the bend. We have walls such as gate pipe.
Hi everyone, my name is ZHAQIA. So I will explain the apparatus for this experiment. Okay, the apparatus for this experiment is inlet valve and two tap manometer tap, outlet valve, and tested pipe section. And methodology. Determine the direction of water inflow and outflow for the tested pipe section and fully open the inlet valve by turning it to anti-clockwise direction of the tested pipe section and close the inlet valve by turning it to clockwise direction for the non-tested pipe section. Turn on the pump and slowly open the outlet valve by turning it to anti-clockwise direction until maximum or fully open, and wait for a while in order to remove any air bubbles for the tested pipe section. Identify the inlet flowing pressure or H1 and the outlet flowing pressure or H2 for the tested pipe section and connect the manometer tabs from those H1 and H2 of the tested pipe section to the two tab manometer H1 inlet and H2 outlet.
Okay. My name is Felix Salim, and now for the first part, we'll calculate the minor head loss and the loss coefficient KL value for each of the pipe components or fittings. So the first fittings is the sudden enlargement, and on the left side of the slide we can have a look at the data that we will use in the calculation part. So we need to calculate the inlet and outlet area of the sudden enlargement to get our KL value, because the KL value for sudden enlargement is not given. And moving on, we need to calculate the velocity, and then only we can calculate our minor head loss. And the value of our HLM is equals to 0.06393 meters. So for the sudden correction, actually it's almost the same for the calculation method as shown in the sudden enlargement. The difference, we can see it at the D1 knot and D2 knot. And the value for this minor head loss is 0.00714 meters. The next fitting is the T-type, and for this type we don't need to calculate the KL value because it's already given in the table inside our lab manual. And for this T-type, we'll use a branch flow threaded tees with a KL value of 2.0. And by doing the simple calculation, we now can have the minor head loss value of 0.1124 meters. For the Y type, we are still using the same KL value as before at the T-type calculations, which is branch flow threaded with KL is equals to 2.0. And from this calculation, we can get our HLM value of 0.1468 meter. Next is the 2 times 45 degree angle pipe. Here we'll use the elbows of regular 45 degrees threaded with a KL value of 0.4, but since we are using
two of these 45 angle pipe, we need to multiply our KL by 2. So the KL value for this calculation is equals to 0.8. And from the calculation that we done, the HLM value is 0.03836 meter. In this 2 times 90-degree angle pipe, we'll be using the regular elbow 90 degrees threaded with a KL value of 1.5, but we need to multiply it by 2 as the previous one. And the HLM value is 0.1469 meters. So for the last part of the fittings, we have the 2 times 90-degree bend pipe. So here we'll be using a long radius 90 degrees threaded with a KL value of 0.7 and multiply it by 2 is equals to 1.4. And by doing the same calculation as before, we'll have a minor head loss value of 0.1062 meters. On the second part of the discussion, we'll discuss the effects of different water flow rates, pipe diameters, and pipe bends on the value of loss coefficients. When we come to the water flow rates, if the water flow rate is high, the friction loss in the pipe will be greater, which then results in a higher loss coefficient. And for the pipe diameter increase, this will reduce the friction that happens inside our pipe and less energy will be lost. Therefore, this will result in a lower loss coefficient. And for the last part, which is pipe bends, when the binding of the pipe is longer, this causes a more gradual turn of the bends, which result in less energy loss and thus the loss coefficient will be reduced. And for our last part of the discussion, we'll briefly discuss on factors contributing to errors or inaccuracy in our experimental data and a possible recommendation to improve the existing results. So there will be 3 factors. The first is presence of air bubbles in the rubber tube and the pipes. So when we are conducting the experiment, there are several times that there is a presence of the air bubbles. And the second factor is the water inside the manometer fluctuates heavily. So it's quite difficult for us to measure the H1 and H2 of the manometers. And the last is parallax error that happens while reading the scale at the manometer. It's because the observer's eyes is not perpendicular to the scale. And for the recommendation part, the first we need to ensure that the air bubbles has completely exit the tube and pipe before we take our experimental readings. And the second is we need to adjust the volumetric flow rate until the fluctuation inside the manometer decreases, so we can easily take note on the H1 and H2 value. And the last recommendation is to ensure that the observer's eye is correctly perpendicular towards the scale. And I think that's all from me. Thank you, and I will pass it to my next colleagues. Thank you.
So now we move on to the results part of this experiment. So as you can see here, we have collected data from 6 types of 6 different types of pipe interaction, which is the T-type, Y-type, sudden enlargement, sudden contraction, 90-degree angle, 45-degree angle, and 90-degree bend. So firstly, we collect the values for H1 and H2, and these values can be observed on the left side of the apparatus setup, which is on the manometer. Then next, we collect the time taken to collect 3 liters of water, and we use a stopwatch to record the time. Then we can proceed to calculate the delta H, which is basically the difference between H1 and H2. Then lastly, we can calculate the volumetric flow rate, which is the volume per time. Then later, for the discussion part, the value of Q is converted into meter cube per second to ease our calculations.
And the last part of this experiment is conclusion. To conclude all of this, we are able to determine the loss coefficient KL and the minor head loss HIM on variety pipes. Minor loss occurs as the water flows through the pipes, which are just not straight, such as sudden enlargement pipe, sudden contraction, Y-type, T-type, 90-degree bend pipe, 90-degree angle pipe, as well as 40-degree angle pipe. Besides that, we also found the correlation of water flow rates, pipe diameters, and pipe bends with the value of loss coefficient KL value, where when the value of the flow rates is higher, the pipe diameters is smaller, and the length of the pipe bends is greater, resulting in higher value of loss coefficient and greater minor head loss. Some mistakes and errors occur affecting the accuracy of the data we obtain, and to overcome this problem, some recommendations have been stated earlier in order to avoid the errors. So that's all from us. Thank you to Dr. Hidayah. Thank you very much. See you again.